Okay, back to Corey Rawson here. I'm going to show you how I collected this data in a separate video, but I hung with a string a mass off here and it spun it. And the more mass I put on, the less time it takes that mass to reach the ground. Okay, so if I hang, let's say, for example, 100 grams off there, it takes 2 seconds to reach the ground from a table height. And the more and the more and the more and the more mass I put on there, the quicker that fall is. But it never gets any faster than the acceleration of gravity. I can hang a Chrysler off here, and it's not going to keep going significantly faster. It's going to follow the acceleration of gravity. And it's only going to get a certain amount of angular acceleration out of that. Okay, and the reason why I bring that up is I have never used a book that didn't mess this up. Okay, so linearly, all this stuff looks like this, which is actually pretty simple, but took me a long time to figure out. So if you drop a mass, it's making a driving force. The tension is dictated by that mass, the dragged mass, and then the leftover is net accelerates that. Okay, that's one way to set it up. If you do the same thing with a spinning mass, you have three things. You have a driving mass here, which is m times g. The wheel is spun by the tension in the string, which is caused by the inertia, the rotational inertia. I'm not paying attention to this today. When you subtract those two off, that still accelerates. So you have to take that driving mass times a, and the books always leave that out. They set these two equal to each other. Okay, so there was an example given like that on page 291 of my book, which is Fawn and Surway and Fawn, the Holt physics book. I don't know what year. Page 291, their problem 2. They said, well, that hanging weight is the applied force and it makes the wheel spin. Well, when you work that out, you had an acceleration of 2,600 radians per second squared. But it can't be that high. Because if you have a falling Chrysler, it's got to accelerate the Chrysler. You need that other term in there. Now, if that falling mass is real small compared to the weight and the size of that wheel, you'll never know. But as soon as that mass starts to get pretty good size, if you're trying to make something go fast, like a trebuchet, you can't leave that term off there. You're going to have a huge error. So when I work that problem, it comes out to, it looks like maybe 115 radians per second or something like that for, I don't know what the acceleration would be. But in this problem anyway, the book answer is 2,600 radians per second squared because they left that term out. The real answer is 131 radians per second squared. So it's way off. So adding in a trebuchet more and more weight works to a point. After that, it doesn't matter how much weight you're going to add because it's only going to fall as fast as gravity is going to pull down that Chrysler.